శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ 2008 లో స్థాపించిన కళాశాలలో NBA, NAC A గ్రేడ్ మరియు ISO సర్టిఫికేషన్ సాధించిన మొట్టమొదటి కళాశాల శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ త్వరలో అటానమస్ కాబోతోంది.
2014లో ISO గుర్తింపు, 2015లో రాష్ట్ర ప్రభుత్వంచే A గ్రేడ్, 2016లో NAC A గ్రేడ్, ఇప్పుడు NBA సాధించిన సంస్థ శ్రీ ముత్తవరపు వెంకటేశ్వరరావు కాలేజ్ ఆఫ్ ఇంజనీరింగ్ అండ్ టెక్నాలజీ.
Good afternoon, students. In the last class, we have discussed about RC phase shift oscillator. So in this class, we are going to discuss about the Wien bridge oscillator, how our opamp is going to work, is going to generate the sinusoidal signal using Wien bridge circuit. So as we have studied the versions of RC phase shift oscillator and as well as Wien bridge oscillator using transistors, and here in this we are going to discuss about the Wien bridge oscillator by using our operational amplifier. By using our operational amplifier, we are going to observe the Wien bridge oscillator, performance of the Wien bridge oscillator. So here you can see this is the circuit of the Wien bridge oscillator, in which this is the bridge circuit. So in this bridge circuit, we are having two different components. Those are the resistor and as well as the capacitor. So in one arm, we have connected this resistor and capacitor in parallel, and in another arm, we have connected the resistor and capacitor in series. So this forms a bridge circuit, nothing but this circuit is going to form a bridge circuit. And this is the feedback network, that is RF and R1 provides the feedback which is connected to the inverting terminal of our operational amplifier, and we are going to take the output. So how this op amp is going to produce the sinusoidal wave, we are going to observe that by using a video lecture. So in the next slide, you are going to observe that how our op amp is going to generate a sinusoidal wave using the Wien bridge circuit, and as well as so what are the drawbacks involved in that, and what are the parameters, what are the different parameters of that circuit. So what is the frequency generated, that is the frequency of the generated signal, that is generated sinusoidal signal. So here the frequency generated by this Wien bridge oscillator depends upon R and C. So the frequency is given by 1 by 2 pi RC. How this is obtained, we are going to observe in the next slide, that is the video presentation will be there in the next slide. So observe that slide, and we are going to see how the op amp is going to generate a sinusoidal signal using the Wien bridge circuit. So now we are going to play this video. Listen.
Videos, we understood the basic working principle of the oscillator, and then we have also seen how to design the RC phase shift oscillator. So in this video, we will see one more type of RC oscillator, which is known as the Wien bridge oscillator. So this Wien bridge oscillator is the harmonic oscillator, meaning that the output of the oscillator is the sinusoidal signal, and it is used for the generation of a sine wave, typically in the range of audio frequency. So if you see the circuit of the RC oscillator, then it will look like this. So as you can see over here, it involves the bridge circuit. Now let me just redraw the same circuit in a different way. So as you can see over here, this resistor R3 and R4 are the part of this amplifier, and these two branches of the bridge circuit forms the RC feedback network. So here the op-amp is used in the non-inverting configuration and the positive feedback is provided to this op-amp through this RC feedback circuit. So now if you see this RC circuit, it consists of a two RC network. The one is the series RC network and the other one is the parallel RC network. So here this series RC circuit acts like a high pass filter, while this parallel RC circuit acts like a low pass filter. So at low frequencies, this capacitor acts like a open circuit, so it does not pass the low frequency signals. On the other hand, at high frequencies, this capacitor provides the very low impedance, so it easily allows the high frequency components. So in a way, it acts like a high pass filter. On the other hand, if you see this parallel RC circuit, at low frequencies, this capacitor will act as an open circuit. So the output voltage at this node will directly appear across this resistor R2. And at very high frequencies, the impedance of this capacitor will be very low. So the output will get short circuited to the ground terminal. So in a way, this parallel RC network will act like a low pass filter. So this RC network does not allow low frequencies as well as high frequencies. But at one particular frequency, the output of the circuit will be maximum, and that frequency is known as the resonant frequency. So in a way, this RC feedback network will act as a notch filter. And if you see the response, then the response of this RC feedback network will look like this. So only at one particular resonant frequency, the output of the circuit will be maximum, and at rest of the frequencies, the output will be minimum. So at this resonant frequency, the phase shift of the circuit will be equal to 0 and the ratio of output by input will be equal to 1 by 3. And if we consider this R1 is equal to R2 and C1 is equal to C2, in that case, this resonant frequency FR can be given by the expression 1 divided by 2 pi times RC. And if this condition is not true, in that case, the resonant frequency FR can be given as 1 divided by 2 pi under root R1 R2 into C1 into C2. So this is the expression of a resonant frequency in a case when R1 R2 and C1 C2 are different. And here the ratio of output by input is also known as the feedback fraction. So here we have a feedback fraction beta is equal to 1 by 3, and to get a sustained oscillations, the A beta of this oscillator should be equal to 1. So in a way we can say that the gain of this amplifier should be equal to 3. Now as we know, this op-amp is configured in a non-inverting configuration, so the gain of the op-amp will be equal to 1 plus R4 divided by R3, or we can say that 1 plus R4 divided by R3, that is equal to 3. That means R4 divided by R3 will be equal to 2. So in this way, at the resonant frequency, feedback fraction of this feedback network will be equal to 1 by 3, and at that frequency, if we want to get a sustained oscillations, then the ratio of R4 by R3 should be equal to 2. So whenever these conditions are satisfied, at that time, at the resonant frequency, we will get the sustained oscillations. So now considering R1 is equal to R2 and C1 is equal to C2, let us design a Wien bridge oscillator of frequency 10 kHz. So here we are assuming that R1 is equal to R2 and C1 is equal to C2, and the frequency of this oscillator is equal to 10 kHz. So under this condition, the resonant frequency FR can be given by the expression 1 divided by 2 pi times RC. Now here, let us assume that C is equal to 0.01 microfarad. So let us find out the value of R for the given values. So R will be equal to 1 divided by 2 pi times FC. That means 1 divided by 2 pi times 10 to the power 4 into 10 to the power minus 8. Or if we calculate the value of R, then it will roughly come around 1.59 kilo ohm. And in this design, the gain of this amplifier should be equal to 2. So let us assume that R4 is equal to 20 kilo ohm and R3 is equal to 10 kilo ohm. And here C1 and C2 are zero point 0.01 microfarad and R1 and R2 are 1.59 kilo ohm. Now what we can do, we can use a potentiometer of 5 kilo ohm for these two resistors, and we can tune these two resistors to the value of 1.59 kilo ohm. So in this way, by using this expression, we can select the values of R1, R2 and C1, C2, and we can design a Wien bridge oscillator of a desired frequency. Now so far we have directly used this expression for this Wien bridge oscillator. So let us derive this expression for the Wien bridge oscillator, and let us also see at this resonant frequency FR why the feedback fraction of this RC network is equal to 1 by 3. So for the derivation, let us assume that the impedance of this series RC circuit is equal to Z1 and the impedance of this parallel RC circuit is equal to Z2. Now for this RC network, the output voltage Vout can be given as Z2 divided by Z1 plus Z2 times input voltage. Or we can say that Vout by Vin is equal to Z2 divided by Z1 plus Z2. Now here Z2 is equal to R2 in parallel with 1 by j omega C2. Or we can say that that is equal to R2 divided by 1 plus j omega R2 times C2. Similarly, this Z1 is equal to R1 plus 1 by j omega C1. So let us put the value of Z1 and Z2 in this expression. So we can write Vout by Vin is equal to R2 divided by 1 plus j omega R2 times C2 divided by R1 plus 1 by j omega C1 plus R2 divided by 1 plus j omega C2 into R2. So if we simplify this expression, then we can write this expression as Vout by Vin will be equal to R2 times j omega C1 divided by R1 times j omega C1 multiplied by 1 plus j omega C2 into R2 plus 1 plus j omega C2 times R2 plus j omega R2 times C1. And further if we simplify it, then we can write this expression as Vout by Vin will be equal to j omega R2 times C1 divided by 1 minus omega square R1 R2 C1 C2 plus j omega R1 C1 plus R2 C2 plus R2 times C1. So after simplification, we will get this expression. Now, like we have discussed, at the resonant frequency, the phase shift that is offered by this feedback network will be equal to 0. That means this term should be equal to 0, so that this j omega will get cancelled out at numerator and the denominator, and the overall phase shift that is provided by the circuit will be equal to 0. So from this we can say that at resonant frequency, this omega square R1 R2 C1 C2 will be equal to 1. Or we can say that omega will be equal to 1 by under root R1 R2 into C1 into C2. That means F will be equal to 1 divided by 2 pi times under root R1 R2 into C1 into C2. Now if we consider R1 is equal to R2 and C1, this expression will get simplified to 1 divided by 2 pi times RC. But for a moment, let us assume that R1, R2 and C1, C2 are different. So now if we consider this condition, then Vout by Vin will be equal to R2 times C1 divided by R1 C1 plus R2 C2 plus R2 times C1. Now if R1, R2 and C1, C2 are equal, in that case, this V out by Vin or the feedback fraction beta will become 1 by 3. But if they are different, then this will be the feedback fraction for this RC network. Now, like we have discussed, for the sustained oscillations, the A beta of this oscillator should be equal to 1, or we can say that the loop gain should be equal to 1. Now, this is the value of beta for this feedback network. So we can say that A should be equal to 1 divided by beta, or we can say that this gain of this amplifier should be equal to R1C1 plus R2C2 plus R2C1 divided by R2 times C1. And if we simplify it, then we can say that the amplifier gain A will be equal to R1 by R2 plus C2 by C1 plus 1. Now here the gain of this opamp will be equal to 1 plus R4 by R3 because it is configured in the non-inverting configuration. So we can say that A is equal to 1 plus R4 by R3 should be equal to this R1 by R2 plus C2 by C1 plus 1, or we can say that this R4 by R3 should be equal to R1 by R2 plus C2 by C1. So this is the condition which should get satisfied for the sustained oscillations. Now if we consider R1 is equal to R2 and C1 is equal to C2, then we will get the condition that we have discussed earlier, that is R4 by R3 should be equal to 2. So in this way, we have derived the expression of the resonant frequency, and we have also seen at the resonant frequency, the feedback fraction beta will be equal to 1 by 3, provided R1 is equal to R2 and C1 is equal to C2. And to get a sustained oscillations, the ratio of R4 by R3 should be equal to 2. So I hope in this video you understood how we can design a Wien bridge oscillator.
Good morning, students. Today we are going to discuss about the instrumentation amplifier. So in the last classes, we have discussed about how op-amp is used as a oscillator. We have discussed in the last class, and you have observed how the op-amp is going to behave as a is going to generate oscillations. So how it is satisfying the loop gain, how the phase shift is going to be satisfied by the top op-amp, and you have seen uh, about amplifiers. You have observed about amplifiers. In the today's class, you are going to observe about the operation of instrumentation amplifier. So in this instrumentation amplifier, so first, what is an instrumentation amplifier? So we are going to discuss about the need for instrumentation amplifier. So where we are going to use this instrumentation amplifier, we are going to see. And when we are considering this instrumentation amplifier, what is the importance of this instrumentation amplifier, and also where we are using this instrumentation amplifier, in which areas we are using in industrial applications. So what are the different components used in instrumentation amplifier, and what is the need for the bridge circuit when we are considering this instrumentation amplifier, we are going to discuss. And here we are using op amp as a differential amplifier. So when we are using op amp as a differential amplifier, so how the gain of the op amp will be, and on which factors this gain is going to depend upon, as well as CMRR. We are going to observe the CMRR of this instrumentation amplifier. In the analysis part, we are going to see all these. And what are the drawbacks in this differential amplifier when we are using this op-amp as a instrumentation amplifier, and how to overcome those drawbacks. So for that, a special ICs has been designed for this differential amplifier to overcome the drawbacks in this differential amplifier. So what are those ICs? And next, what is the modification done in instrumentation amplifier circuit? So what is the buffer? So as we have discussed in our last classes, buffer, about buffer, that is unity gain follower, nothing but need for buffer amplifier in our instrumentation amplifier. And next we are going to see, if you use buffer, how to improve the gain of this instrumentation amplifier. What are the factors affecting the performance of this instrumentation amplifier? And then for overcoming the drawbacks in instrumentation amplifier using buffer, so we are going for non-inverting amplifier instead of buffer amplifier. And when we are using non-inverting amplifier, the CMRR will be improved, but the problem with the gain, there is a problem with the gain. So we cannot modify the gain of the circuit. Gain of the circuit is fixed. So to improve or to modify the gain of the circuit, we are going, and to modify the gain of the circuit as well as to improve CMRR further, so we are going to place a resistor. So we are going to study about that resistor, need for that resistor, and then we are going to see the analysis part of this final instrumentation amplifier. So in this class we are going to cover all these topics. So in the next slide you are having, we are going to watch a video on this alpha, what we have discussed now, on these all the points.
In many industrial applications, it is required to measure the certain parameters like temperature, flow, humidity, etc. And these parameters are measured using the transducers like RTD, strain gauge, and thermocouples. So these transducers convert the measured parameter into the electrical signals. And many times to convert this measured parameter into the electrical signals, these bridge circuits are used. For example, if we take the case of RTD, in RTD, as the temperature changes, the resistance of RTD will also change. So if we connect this RTD at one of the arm of this bridge circuit, then the resistance of this particular arm will change according to the temperature, and accordingly the voltage that is generated at particular node will also change. So if we measure the voltage across these two terminals A and B, then the voltage will change according to the temperature, and this generated differential voltage can be amplified using the differential amplifier. Now, many times in industrial applications, it is quite possible that the location where these measurements are carried out and the locations where these sensors are deployed are quite far away from each other. So, in this case, it is quite possible that the noise or the interference signal will get superimposed over the measured signal. And to avoid the problem of this noise or interference, many times the signal is measured using the differential measurement technique. For example, if we take the case of this bridge circuit, the output that we are getting through this bridge circuit is also differential signal, and this differential signal further can be amplified using the amplifier. So as you can see over here, the output of this bridge circuit is given to this differential amplifier. So the advantage of this differential amplifier is that whatever common mode noise or the common mode interference signal which appears at the two terminal of this differential amplifier should ideally get eliminated, and only the differential signal across the two terminal should get amplified. So if V and VB are the voltages that appears across the two terminal of this differential amplifier, then the output of this differential amplifier can be given by this expression. So at the non-inverting terminal, the voltage will be equal to this R4 divided by R3 plus R4 times the voltage VA, and that voltage will get amplified by the factor of 1 plus R2 divided by R1. Similarly, the output voltage, because of the input at this inverting terminal, will be equal to minus R2 divided by R1 times this voltage VB. So if we rearrange these terms, then we can write this same expression like this. Now here, if we assume that the ratio of this R4 by R3 is equal to this ratio of R2 by R1, in that case, the output voltage can be given by the expression R2 divided by R1 times the voltage VA minus VB. So in this case, as you can see, the output voltage Vout will be the difference between the two input signals multiplied by the gain of this circuit. Now so far we have assumed that there is no common mode voltage present at the input terminals. But if common mode voltage is also present along with the differential input voltage, in that case, in general, the output voltage of this differential amplifier can be given by this expression. So the differential input voltage will get amplified by the differential gain, while the common mode voltage will get amplified by the common mode gain. Now, in this case, suppose if common mode voltage is also present, then we can say that the voltage VA will be equal to this common mode voltage VCM plus VD by 2. And likewise, this voltage VB will be equal to VCM minus VD by 2. So, if we assume that the ratio of R4 divided by R3 that is equal to R2 divided by R1, in that case, the output voltage Vout will be equal to R2 divided by R1 times this voltage VA minus VB. And if we put these two values of VA and VB, then the output voltage Vout will be equal to R2 divided by R1 times this differential voltage VD. So if we assume that this opamp is ideal, in that case, this circuit should amplify only differential input signal and it should reject the common mode signal. But even if we assume this opamp is ideal, then also because of the mismatch between these resistor pairs, the common mode signal will also present at the output terminal. So even if there is a 1% error in any of the resistors, then also the common mode rejection ratio will get affected and the common mode signal will present at the output terminal. And this particular scenario will become critical when your differential input signal is very small and the common mode signal which is present at the two input terminal is larger than the differential signal. So let us take some values of these resistors as well as the input voltages, and let us see how the mismatch between these resistor pairs can affect the output voltage. So here let us assume that the resistance R1 and R3 are 1 kilo ohm, while the resistor R2 is equal to 10 kilo ohm. And here we are assuming that there is a 1% error in this resistor R4. So instead of 10 kilo ohm, the value of this R4 is equal to 10.1 kilo ohm. And the differential input to this differential amplifier is equal to 10 millivolt, while the common mode input to this differential amplifier is equal to 1 volt. So in this case, let us find out the output voltage of this differential amplifier. Now we know that the output of this differential amplifier can be given by this expression. And if you put the value of these 4 resistors in this expression, then we will get the output voltage Vout as 10.009 times this voltage VA plus 10 times this voltage VB. So now let us put the value of this VA and VB in terms of this common mode voltage and the differential input voltage. So if we put the value of this VA and VB, then we will get the output voltage Vout as 0.009 times the common mode voltage plus 10.0045 times this differential input voltage. And if we compare this expression with this expression, then we can say that the common mode gain of this circuit will be equal to 0.009, while the differential gain will be equal to 10.0045. And if we find the common mode rejection ratio, that is the ratio of this differential gain and the common mode gain, then that will be equal to roughly around 61 dB. So ideally, this common mode rejection ratio should be infinite, but because of the slight mismatch in any of this resistor, the value of this common mode rejection ratio has been reduced to 61 dB. Now let us see how it will affect the output voltage. So here, the value of this common mode voltage is equal to 1 volt. So this common mode voltage will get amplified by this factor, and because of that the output voltage Vout will be equal to 9 millivolt, while the differential input to this circuit is 10 millivolt. So it will be amplified by the factor of 10. So at the output we will have a 9 millivolt because of this common mode signal and almost 100 millivolt because of this differential input signal. So as you can see, 9% error will get introduced in the output voltage, and it will further increase if there is a mismatch between more than one resistors, or if the common mode signal that is present at the input terminal is more than 1 volt. So in that case this error will further increase. So as you can see over here, the mismatch between the resistors can affect the output drastically, and it can reduce the common mode rejection ratio of this differential amplifier. So the one way to solve this problem is to use the monolithic ICs for this differential amplifier. So one can use readily available differential amplifier ICs like AD629 and INA106. So in these ICs, the resistors are fabricated in the IC itself, and in these ICs, the ratios of these resistors are matched quite accurately. So using these ICs, you can increase the common mode rejection ratio and you can minimize the error in the output voltage. So even if we use such monolithic ICs for this differential amplifier, then also we will face the problem of this input impedance, because if you see over here, the input impedance at this inverting terminal is equal to R1, while the input impedance of this differential amplifier at this non-inverting terminal will be equal to R3 plus R4. So if these input impedances are comparable to the resistance of this bridge circuit, in that case the differential input that is available at the two input terminal will also reduce. So it is highly required that the input impedance of this differential amplifier should be very high. So one way we can solve this problem is to use the buffers before the inputs. So if we use the buffer circuits, then we can increase the input impedance of this differential amplifier. So in this way, by using these buffer circuits along with these monolithic ICs, we can solve the problem of this input impedance as well as the problem of this mismatch between the resistor pairs. But the problem with these monolithic ICs are that the gain that is provided by these ICs are fixed. So you cannot change the gain of this differential amplifier. And in your application, if you want to change the gain, then using these ICs you cannot change the gain. So one way we can avoid this problem is by using the non-inverting op-amps instead of these buffer circuits. So the same circuit can be represented like this. So in these circuits, the initial gain can be provided by these non-inverting buffers. But the problem with this circuit is that along with the differential input signal, the common mode input signal will also get amplified. So you will not get any improvement in the signal to noise ratio. Apart from that, in this circuit, you also need to match these four resistors, because if there is a slight mismatch in these resistors, then once again the common mode rejection ratio of this circuit will get compromised. So these are the problems that you face with this differential amplifier circuits. And the one way we can avoid this problem is by using the instrumentation amplifier. So in terms of the circuit, if you see, there is only one difference between this circuit and this circuit. So over here, this resistor RG is common between the two op-amps. Now the advantage of this configuration is that only the differential input signal will get amplified by these op-amps, while the common mode signal will pass as it is. So this instrumentation amplifier is available in a IC format, and except this resistance RG, all the resistors are fabricated internally. And because they are fabricated internally, they are highly matched. So just by connecting this resistor RG externally, we can set the gain of this instrumentation amplifier. So for this configuration, if we assume that this R5 is equal to R6 and the ratio of this R4 by R3 and R2 by R1 are matched, in that case, the output voltage Vout can be given by this expression. So now let us derive this expression, and during the derivation, let us also understand how this circuit will amplify the differential input signal and it will pass the common mode signal as it is. And using this, how we can improve the common mode rejection ratio of the circuit. Now in this circuit, let us assume that the voltage at this node is equal to VB dash and the voltage at this node is equal to VA dash. So the output voltage Vout can be given by the expression R2 divided by R1 times this voltage VA dash minus VB dash, provided the resistance R4 divided by R3 that is equal to R2 divided by R1. So first of all, we need to find the difference between this VA dash and the VB dash voltages. Now, if you observe this circuit, the voltage at this node will be equal to VB, because here we are assuming that all the op-amps are ideal. So whatever voltage that appears at this terminal, the same voltage will also appear at this terminal. And likewise, the voltage at this node will be equal to voltage VA. So from this we can say that the current that is flowing through this resistor RG will be equal to VB minus VA divided by this resistance RG. And let us say this current is equal to IG. So we can say that current IG will be equal to VB minus VA divided by this resistance Rg. Now the same current Ig will also flow through this resistance R5 and R6, because here we are assuming the op-amps are ideal, so no current is flowing into the op-amp terminals. So we can say that the same current Ig is flowing through this resistor R5, Rg and R6. And using this we can find the difference between this voltage VB dash and VA dash. So we can say that VB dash minus VA dash will be equal to this current Ig times resistance R5 plus Rg plus R6. And if we assume that this resistance R5 is equal to R6, in that case we can say that VB dash minus VA dash will be equal to Ig times 2 times this resistance R5 plus Rg. So now if you put the value of this current Ig from this expression, then we can write VB dash minus VA dash will be equal to VB minus VA multiplied by 1 plus 2 times R5 divided by this resistance Rg. Or we can say that VA dash minus VB dash will be equal to VA minus VB times 1 plus 2 times R5 divided by this resistance Rg. So this is the voltage that will be present between the two input terminals of this differential amplifier, and the output voltage Vout will be equal to R2 divided by R1 times this voltage VA dash minus VB dash, that is equal to R2 divided by R1 times 1 plus 2 times this resistance RF divided by Rg times this voltage VA minus VB. So in this way, this differential input will get amplified using this instrumentation amplifier. So now let us also understand how this instrumentation amplifier will pass the common mode voltage as it is, and it will only amplify the differential input signal. So now let us say the common mode voltage VCM is present at these two terminals. So the same voltage will also present at these two terminals. Now because the voltage at these two terminals is same, so no current will flow through this resistance Rg. And because of that, we can say that the no current is also flowing through this resistor R5 and R6. And in a way we can say that the same voltage is also present at this terminal and this terminal as well. So we can say that for the common mode voltage, these two amplifiers will act as a buffer or a unity follower, while it will amplify only the differential input signals. So in this way, by using this instrumentation amplifier, the common mode rejection ratio of the circuit can be further increased. And this instrumentation amplifier is particularly useful in an environment where the differential input signal is very small and the common mode input signal which is present at the two terminal is larger than the differential input signals. And that is why this instrumentation amplifier is preferred over the differential amplifier in industrial as well as the test and measurement circuits. So I hope in this video you understood the importance of this.
So from this video, we have understand the importance of this instrumentation amplifier, and how the different disadvantages we can overcome in this instrumentation amplifier. As we have observed that here in this circuit, when we are using in industrial applications, the signal generated by the transducers, which is nothing but a thermocouple or um, or a flow meter, so which is going to generate a low voltage signals, which cannot drive the other circuits, which cannot be able to drive the other circuits, then this instrumentation amplifier is going to be used there. So because of that low voltages, so we need a two differential amplifiers here, So we what we have placed the differential amplifiers will amplify the signal first, and then it will be given to the third op amp. So which is the first two op amps here going to operate as a non-inverting amplifiers, and the third op amp is going to act as a differential amplifier. So the first two op amps is going to amplify the signal what we have given, that is having a low strength, and then that will be given to the differential amplifier, which gives the output accurately. So in this way, uh, the instrumentation amplifier performs its functioning. Thank you, students.